Um, Morning again. Welcome back to our class. Um, we would have started our study of the choppers. Those are the DC-DC converters. We look at the buck, look at the boost, then look at the buck boost. Our last class we um we look at the boost converter, but we did not work a problem on the boost converter. So I will let me just go to that the lesson. Um, all right, so we're supposed to go through this problem on the buck boost. All right, you can look at it and give it a try. All right, so you have a buck boost circuit and it has these parameters. Just they are told that the source voltage is 24 volts, the duty cycle is 0.4, and the load resistor there is 5 ohm, inductance is 20 microhenry, and you have a capacity of capacitance of 80 microfarad. And the switching frequency that you're using is 1000 kilohertz. You also determine the output voltage, the inductor average maximum and minimum values, and also the output voltage ripple. All right, so this is a fairly simple question. You just applying the formula, right, that relates to the buck boost, that is the buck boost converter, right? And you will recall that for your buck boost converter, the output, this not right, the buck boost characteristic equation that relates the input voltage and the output voltage given by output voltage equal to the input voltage, or we say source voltage, that would be into the duty cycle over 1 minus the duty cycle. Right, so that's the equation. So you can make the substitutions that are given, right? Very important thing here that I've left out. Sorry, it is always negative. Yeah. So right, so there's a negative there. So we can go ahead with the substitution. Right, so input voltage, that's 24 volts, and 1 minus your duty cycle, that is 0.4 into, I don't know why I'm doing this, duty cycle 0.4, 1 minus 0.4 here, right? What do you get? It's always negative. There's negative something. Just work that out for me. Right, so 1 minus 0.4, that's what, 0.6. So we have 0.4 over 0.6. That's 4 over 6. 6 into 24. That's 4. 6 minus 16. So this is 16 volts. 16 volts. Right? So it's always negative. Right? There's always a negative there. Alright, so for the next part we'll ask you for the inductor current. That's the maximum as well as the minimum, right? So the average as well as the maximum and the minimum. All right, so I think we had to work out the formula that we can use, right? So your inductor current, you'll recall, given by what's the expression again? The input voltage multiplied by the duty cycle and divided by the resistance into 1 minus the duty cycle square. Towards that. And so we can make the substitutions here. So the input voltage was, I think, what, 24 volts, and your duty cycle 0.4, and your resistance 5 ohms. Zero 0.4 square. You can work that out. What do you get?
5.3.
So that's what, 5.33 amperes. Okay. Let's write this properly. 5.33 amperes. All right, so that's the average current. All right, so we can now find the maximum and the minimum, right? But in doing so, recall that we just need to add half of that change in current to that average current and subtract half, and we'll be able to get the maximum and minimum, right? So that delta IL, let me just write it like this. Delta IL, so that was equal to the input voltage times the duty cycle, right? And multiplied by the period, right? And we divide this by the value of the inductance. Alright, so you can make the substitutions here. So this would be input voltage. Alright, so what we're going to use for the period, we know
1 over the frequency.
right, we know that will be just 1 over the frequency, right? So if we make that substitution of 1 over f, right, we can see clearly that this is just the input voltage times duty cycle divided by the inductance times the frequency. Right, so we can proceed with the substitutions. All right, so input voltage, it's 24 times the duty cycle, 0.4, and divide with inductance. Inductance, we say that is 20 microhenry, and the frequency 100 kilohertz. So we make that substitution 20 micro 10 to the minus 6 and 100 kilohertz times 100 times 10 to the 3. Oops, there's something here. That's 100 kilohertz here. Alright. Right, so when you work that out, this comes to
Is that 4.8?
4.8 amperes. Alright, so we know to get that maximum and minimum that they asked to find maximum, you just need to add and subtract half. So our maximum right to just be equal to that inductor current plus multiply like that. Plus half. Right? Can work that out. And your I mean would be minus right. You can work that out and tell me the answer that you get.
For the I got 7.73.
Alright, that's on right. 7.33.
73.
7.73. Right. Ampere, and the minimum
2.9.
2.9.
3.
Alright, 2.93 amperes.
Amperes.
So the next part ask us to find the ripple. Alright. So let's just divide it. So this is A, A, B, and then we have part C. So for the ripple, we know that is just that change in our output voltage, that ratio. So that's the ripple, and just the change in that output voltage to the output voltage, and that's equal to the duty cycle, as you recall, divided by the resistance multiplied by the capacitance multiplied by the frequency. And your duty cycle is 4. Your resistor, suppose 5. Resistor is 5 ohms. What happened here? I just switched up and I lost it. I don't know what happened. I don't know why this just got deleted. Anyhow, let me just write it back. See, just huh? Why this thing jumping up and down? B, C. Sorry about that. This thing. Don't know why it was jumping up and down this morning. So we have D over R and C times F. Make the substitutions. That will be 0.4 over to be 5 times the capacitance. We said that was what? Hope it don't disappear. 80 microfarad. Oh my, what the hell happened here? Just switch up on it. What I wrote just vanish. I don't know why that is happening this morning. Okay, now I'm gonna write it back. C R E R C F, and that would be 0.4 over 5 times 80 times 10 to the minus 6 times 100 times 10 to the 3 What do you get?
I got 10,000.
10,000.
Yeah.
That can be right. 0.4 divided by 5 times 80 times 10 to the minus 6 times 100 times 10 to the 100 kilohertz.
0.0.
Okay, 0.01. So that's about that's what, 1%, right? So in percentage, that would be 1%. 1%. Mm. All right. 1%. Oh no, it's gone. So 1% here. All right. So let's move on to the next one. I don't know why that was happening. All right. So I think we've completed that question. Let us write the answer here so that when I submit this slide, you will have it. Oh, why that happened? Um, you could always view the present. I don't want to waste no more time there. All right. So the next part was control of this converter. You would probably have seen in the circuits we just would have, let's say, for example, when we look at this the buck converter. I would just draw a simple switch here, right, and I show you that it's controlled by some pulse width modulation by drawing this signal associating with it, right? So there's more to it. So we're going to look at this control, right? How do we get this pulse width signal, right? This is one way it can be pulse width modulated signal. This is one way it can be generated. Those of you who are doing power electronics or industrial electronics or have done it already, they'll come across this concept of generating pulse width modulation type signals. So we look at this block. Let us say we get in our control signal and we feed it into a comparator where we compare it with some sawtooth waveform. Right, so this is our sawtooth waveform. That's what we are comparing it with. And the output here is some DC level. Let us say the solid in the first instance. Let's look at the first control level. Of course, we could adjust by adjusting our V out to some desired level. We're able to set up that control for the comparator. So let's look at the dotted line first, right? So output or first control, let's call it control 1, that's given by the dotted line here. So comparing it with the sawtooth waveform that we apply at the input of the comparator. So how it works, all right, so the control signal is above the sawtooth waveform, right, when we compare it, so it sets it high, right? So this would be the switching point, so that would be one switching point, another switching point, another switching point, another switching point, one there, one here, and one here, right? So we're just comparing, right? So if the control signal is above the sawtooth waveform, then the output is going to go high. So as I can see in the first instance, the sawtooth waveform is below the control signal, so it goes high. In this region, we have now the sawtooth waveform going above it, so it goes low, right? As you can see here, right? When we move over between these two switching points, what we are now seeing is the control signal being above the sawtooth. Here's the sawtooth, it's above, the output goes high, right? So if you continue, right, you see that trend, right? So the dotted line is showing you the width of the pulse. Now, if we want to change the desired level, let us say we bring this control signal down by adjusting the desired input to this first comparator that we have here. We could have it being the solid line just below the dotted line. Yeah, so that would be our second control. Now, and we can do the same thing. We identify the switching points. So this is one switching point, another one. Right? Let us do three of them so that you can see by now you have the idea. So again, let us look at what is happening here. At this switching point, the signal is above the sawtooth. Sawtooth, as you can see, is below that second control signal. So this would be the width. As I say, it's a smaller width when compared to the first control signal. Right, let us continue. Right, so here, now we see that the sawtooth waveform rises above that control signal 2. So it then goes low. The output of this comparator will go low. Right? Now, as we continue, see now the sawtooth waveform is below the control signal, right? So it now, the output now goes high. So what you're seeing basically here is the width of the pulse being changed, right? So by just varying this control signal, we're able to vary the width of the pulse, right? So this is what we refer to as our pulse width modulation, right? So this is how we actually generate that pulse width modulated waveform. All right, so now our DC-DC converters, we could have them being isolated. right? By simply using what we call an isolation transformer. You can have two types, switch mode and the linear type. Linear type you would have been familiar with when you're in first year, or maybe in high school when you built your first power supply, right? Now, when we look at the advantages of that switch mode over the linear power supply, you realize that you can realize efficiencies between 70 and 95%. And generally, you will see a reduction in the size and the weight of your power supply, right? Mainly because now you're using semiconductor devices to build your power supply. When we look at the disadvantages, as you can see, the design is quite complex, right? And also, there's a problem with the electromagnetic interference. That's what I have here as EMI. Right, so when you're designing the circuit, you also have to choose switching frequencies higher than the acoustic range of 20 kilohertz. Right. Also, when we look at the different types of switch mode power supply that we can have these fly back, forward, push pull, and we could have a bridge type, right? And that can be a half bridge or a full bridge type, right? We will not get into these types for this course, but just to let you be aware. All right, just to show you the two. Remember earlier on I referred to the linear power supply. You are pretty much familiar with it. Also the switch mode power supply. So the first one that you're looking at, schematic here. This is the linear power supply. Pretty simple. You have your input signal, your transformer, and you would have your set of diode rectifier and a filter, right? At the first stage. And for the second stage, this part, this is where you try to incorporate some kind of regulation, right? So it's a regulated output, right? So you don't want it to exceed the desired ratings that you design it for. So you build some regulation into some kind of control into your power supply. So here is just a series pass transistor, and of course you design some feedback mechanism here through your comparator. Of course, the output is not what it's supposed to do, is not what it is at, and compared to that desired reference, you can make adjustment to the base of the transistor that's to force it to that desired output. Right? When we look at the the switch mode power supply however, as you can see, we still have that isolation, right? This is our isolation transformer, right? For the linear type, we have our isolation transformer here as well. All right, so we put there a filter. Remember, the electromagnetic interference is an issue, so we need to be able to take care of that. We have our filter here. Of course, at this point, it's not regulated, so it's the DC-DC converter that you will build that will be doing the regulation, right? So as compared to this, let's compare the linear circuit, right? Up to this point, right, it's unregulated, right? So over here, in this part, that's where you have the regulated output, right? For your switch mode power supply, your regulation, your isolated supply is regulated in this section where you have your DC-DC converter, your pulse width modulation circuitry, right? So you would have constructed your DC-DC circuit, and as you can see here, the output, if it is not what it is supposed to be, it's not that desired, it is not at that desired level, then it is fed into some comparator compared to that reference voltage that you so desire, and the error signal is sent to your pulse width modulator controller, which then will be adjusted so that the switch can operate accordingly, forcing that output to your desired level, right? So here the width of the pulse is just being adjusted, right? So that it can be forced to your desired output level, right? So that's what this is doing. I think we finish here. Let me just do you have any questions?
Yes, sir. You can go the last one.
So let me just go back. Go back to the
The last.
yes.
Yes, sir. The drive, what would that comprise of? And also, if the gate is off for the transistor, meaning it's not switched on, what would happen if excess voltage is applied to the collector part of the transistor?
Hold on, let me take your question slowly so to understand it. Right, so the first question you're asking is about the linear supply.
The base gate, yes.
Right. You're asking what would happen if you have a larger voltage.
No, I'm saying what is it comprised of, the base gate drive?
The base gate drive.
Yes, sir.
This part.
Yes, sir.
Remember earlier on we studied drive circuits.
Yes, sir.
Right. It could be any of those kind of drive circuits. that you use.
Okay.
Right.
And the next part of the question is if the gate is off and there's excess current applied to the collector, what will happen? It will let through some of the voltage.
If they drive, say that again.
If the gate is closed, like there's no current applied to the gate to switch it on.
Right, right.
Yeah.
So you
And
mean if this transistor is off,
yes, sir.
right? So this is off.
Yeah, and excess voltage is applied to the collector. Would it let through some amount of current?
This is off. If you are going to have and there is some voltage. That's what you're saying.
Yes, sir.
But as I can see here, there's a mechanism to take care of that, right? So if this should not be what it's supposed to be, then it's compared with the reference voltage, and it will then force the drive circuit to let it be at the desired level. Right, so this in itself is a protection mechanism that is built into the design. I don't know if I'm answering a question.
Yes, sir. Yes.
Right, so that's basically what is happening. So it's not like it will get high and damage the transistor, because that is why we have it regulated. So with your regulated type supply, you guard against that kind of situation.
Okay, thank you, sir.
All right, you're welcome. All right, any other question? All right, let me